Okay, we're going to talk about exponential growth and exponential decay and how to graph these things and how to use these kind of models for situations in life. So for any exponential equation, y equals a to the x, where a is greater than 0, the y-intercept is always 0, 1. So on our graph, we can always plot 0, 1 because anything to the 0 power is 1. The graph of our function lies entirely above the x-axis, since a positive number to an exponent is always greater than 0. And what that causes is it causes us to have an asymptote that's at the x-axis. So if I draw a quick sketch, it goes like this. And we have this horizontal asymptote at y equals 0. If a is greater than 1, then as x increases, so does y. That's this kind of graph. It's called positive exponential. If a is between 0 and 1, then as x increases, y decreases. This is called a negative exponential, or it's also called exponential decay. It would look like this. That's when a is between 0 and 1, when it's a fraction. So we're getting this going down. We're still crossing at 0, 1. So let's take this and make it a little bit bigger. So let me get rid of that. I'll bring this one in. So now, instead of y, we say n, the number of things that we have, equals b times a to the t over k plus c. This is like y equals a to the x, just a little bit more complex. Now we have a leading coefficient in front of the power. We've got a little bit more to the exponent, and then we're adding something. So the background level, in other words, the starting amount, the amount that's expected to be there, is going to be this c. If you think back to function transformations, that is our vertical shift. And we now don't have an asymptote at the x-axis. We have an asymptote, a horizontal one, at n equals c. We could also say that it's y equals c, but we're defining our dependent variable to be n instead of y. Our initial value is b plus c. So that's when time equals 0, how much are we starting with? B plus c. We're putting in 0 here. A to the 0 is 1. So that becomes 1. B times 1 plus c. K, this denominator, is the amount of time taken for the difference between n and the background level to increase by a factor of a. We'll look at what that means in a problem in just a minute. And again, if a is greater than 1, exponential growth. If a is between 0 and 1, we have exponential decay. Let's get into some examples. So here we have a temperature problem. It's given to us by Newton's law of cooling. We have this equation, 24 plus 72 times 0.6 to the 3t. What's the initial temperature? Well, we can figure that out if we're not sure by plugging in t equals 0. So then we have 24 plus 72 times 0.6 to the 0. 0.6 to the 0 is 1. So 24 plus 72. Our initial temperature of this liquid is 96 degrees Celsius. Find the temperature of the liquid after 2 minutes. Well, to do that, we plug in t equals 2. 24 plus 72 times 0.6 to the 3 times 2. So it's really 24 plus 72 times 0.6 to the 6. And that's something that we can plug into our calculator. I'm going to read this off of my graph in just a couple minutes. How long does it take the liquid to cool to 26 degrees? Well, for that one, we're replacing the big T instead of little t. We're looking for little t. So 26 equals 24 plus 72 times 0.6 to the 3t. Now, how do we solve for a variable that's in the exponent? Well, to do that, we can use logarithms, but I'm going to go to my graph. I'm going to take and use my graph to solve this equation. So let's go to our calculators. I've typed in the equation already, right there, but I can't see it. So what do? Well, I need to rescale my axis. I need to go up quite a bit higher. So let's go up to 100 and see what we can see. Okay, there we go. There's my equation. And then I'm going to go and put in 100 for x also. So there we go. We have a sharp drop off, then it levels out. Notice you can really see this asymptote here. We have that asymptote, and that asymptote is at 24. And I guess before I go any further, what temperature does the model predict the liquid will eventually reach? Well, it's going to reach that asymptote. It's getting closer and closer to it. 24 degrees Celsius. Also note that this is an exponential decay model because the base is between 0 and 1. So anyway, back to part C. How long does it take to get to 26 degrees? So here's what we're going to do. I'm going to add a table. Go to Menu, Choice 7, Split Screen Table. So I want to know 26 degrees. Oh, shoot, it's not there. Gosh, what could I do? First, let me make the table go away. I'm going to press Tab, and I'm going to put in another equation. I'm going to put in that 26 that I'm curious about. There we go. Now, I want to know, really, where do these things intersect each other? So I'm going to go to Menu, Analyze Graph, Intersection. So how long does it take to become 26 degrees? 2.34. Well, 2.34 what? 2.34 minutes. And we'll look at another example in the second video.